Hello, for this video we would be talking about the analysis of truss using method of sections this time. So if you have watched the previous pre-recorded lecture that was about method of joints, so we actually have solved for our bar forces already. So this would be the bar forces of each of the elements of this truss right here. But what if you're only concerned with a certain bar member? So for example, that you only want to know the bar force of this member BC right here. Is it possible to know this bar force right here without solving for the bar force of member AB, member AB, member BE, and whatsoever? So there is actually a way. And of course, since you already know where we are going in this, so that way would be the method of sections. So in the idea of method of sections, the idea of method of sections is that you would be dividing your truss into two sections. So for example, once again, that I am only concerned with this member right here. So I would be cutting this truss right here in this manner. So by that, I would just be erasing it. So as simple as that. But take note, guys, that if you would be cutting trusses, if you would be passing a cutting plane onto it, this trusses right here would be converted into forces. So this would be force BC, this would be force EC, and this would be force EF. And unlike in method of joints, instead of analyzing them per joint, you would be analyzing them per section. So since we have already divided our truss right here into two sections, you would now be choosing in what section you would be solving. So may it be this section right here, or may it be this section right here. Okay, but before that, I would be showing you a case wherein method of section is advantageous over method of joints. And as you know, method of joints is quite simple, wherein you are just to analyze joint per joint to get the bar forces of each member. Okay, so suppose that you have this truss right here, and as you can see, there are a lot of members in it. So for example, that you want to get this bar force right here, so that is your only concern. And if you are to use method of joints in this truss right here, you would be starting from here or starting from here. And it is quite logical to start in this in this support right here. So if you would be getting the bar forces using this joint right here, you would be getting this, this, and this. And after getting the bar forces of those members, you would be continuing in this joint right here, where you will be getting this, continue with this joint right here, and you would be acquiring this up until you reach this joint right here for you to get this bar force right here. So that's plenty of work just for this bar member right here. And this is where method of section is advantageous. In method of sections, what you would be doing is just you would be cutting this plane right here, this truss right here in this manner. If you are to cut it, this would be converted into forces. So there. And once that you have converted the members into forces, you would now be choosing on what section you would be analyzing. So if you are to analyze this, so we are to analyze this part right here by applying our equilibrium equations. So let's just go back to this example right here. But take note, guys, that in the last pre-recorded lecture, I have named this as AD, and it would be more appropriate if I name this RD instead. So RD, or the reaction in D, or you can name it as DV instead, or D vertical. But it is more appropriate once again to name it as RD, which is the reaction at D, because if we are to name it as AV, we don't have an AH. Okay, so I would be explaining first why it is more appropriate to name this as RD. So if this is to be D and this is to be A, so this is to be RD. So RD. And as you remember, I have named this as AH, AV, and AH respectively. So this is to be AH. So why is there an inconsistency in the nomenclature? Because in RD, so this is to be your reaction at D. So why didn't I name this as RA? Because basically your AH and your AV is the components of your RA. So by that, your true reaction here, in if you are to have a hinge, is to be in this manner right here. So this would be the true reaction of your hinge, where the magnitude of that would be your RA. So once again, your AV and your AH are just your components of your RA. So it would be as simple as that. So once again, it is better for you to name it as RD. Okay, so if we are to solve for these three members right here, so once again, I would be choosing which part I would be analyzing. So may it be this part right here, or may it be this part right here. I want to solve for this bar forces right here using this section in the left. Okay, so if that is to be the case, I would now be erasing this. And I would just be solving for this. I have now chosen this section right here as the one that we would be analyzing. Okay, so once again, I want to solve for member BC. This is to be member EC, and this is to be member EF. So if that is to be our system right now, I would be applying our equilibrium equations. Okay, so you can either get this equation right here, the summation of forces horizontal is equal to 0, the summation of forces vertical is equal to 0, or the summation of moments along any point is equal to 0. Okay, and if I want to get the bar force of this EF right here, so it would be up to you on your technique, but in my case, I want it to be like this. So for this bar force right here, I would be applying in this point right here, so that member BC and member EC wouldn't be included in the equation because they would have no lever arm in it. Okay, so once again, if I would be getting the moment at C, so summation of moment C is equal to 0. Let's say that clockwise is to be positive. So this is to be point C. Okay, so what are the forces that would make, what are the forces that has a moment if you would be applying it to C? So that would be this 75 kilonewton force right here. So 75 kilonewtons times the lever arm, and the lever arm is the perpendicular distance from your point to the location of this force right here. So that is to be, so looking back at this, that is to be 4 meters, or this part right here. Okay, so that is to be 4 meters. So is it negative or positive? So this would be negative, since that is to be in counterclockwise manner. Okay, so what else? So as for BC and EC, they would be having no lever arm since they are concurrent to that point. So we would be including this EF right here. So EF times lever arm, and our lever arm is this height right here, or the perpendicular distance from point C to the force of EF, which is this part right here. So it would be this, since this is to be your force. So that is to be 3 meters. So 3 meters. So is it positive or negative? Once again, it is negative, since this is to be your force and this is to be your point. So it would be in counterclockwise manner. So what else? So we have this AV right here. So AV times what would be the distance, that is to be 4 plus 4. So it would be 4 plus 4. This distance right here, which is the perpendicular distance from point C to this force AV right here. So that is to be 8 meters. So is it positive or negative? So it is to be positive, since it is in the clockwise manner. So that is to be equal to 0. And solving for EF. So by the way, our AV is actually equal to 66.7. Okay, so from that we can now solve for EF. Okay, so this would be so transposing the red and the green numbers right here to the other side. So that would be positive 75 times 4 minus 66.7 times 8. So basic algebra. So that would be negative 233.6. So 3EF is equal to negative 233.6. So for us to get the value of EF, divide both sides by 3. And from that, our bar force EF is to be negative. So divided by 3, negative 77.86. So as simple as that, we have already solved for this value right here without solving for these values right here. Okay, but if we are also concerned with this bar force right here, we can use any equilibrium equation that we know. Or using that, we can get the moment about this point so that the moment arm of both EC and EF would be 0 and we would be solving for bar force BC. So if you didn't understand that, let's just copy this to the next slide. And I would be erasing this. We already know the value of EF. As for the values of BC and EC, we don't know it yet, so we would be solving for them. So for us to get the value of BC, we can either apply the summation of forces horizontal and summation of forces vertical, or we can once again get the moment about a point. So where would that point be in such a way that your BC would be the only one in the only variable in the equation? So I would now be getting the moment on this point right here. So bakit sa point na yan? I chose this point right here because if we are to get its moment, the moment about that point, the lever arm for both EC and EF would be equal to 0. Okay, so from that, the summation of moment about point E is equal to 0. So let's say once again is that it is clockwise positive. Okay, so from that, our AV or 66.7 kilonewtons times the lever arm, so that would be 4 meters. So would it be positive or negative? So it is positive since it is clockwise. So what else? That would be BC. So plus BC times 3 meters. So lever arm 3 meters. So what else? So basically wala na. So that is to be equal to 0. Okay, now solving for BC using this equation right here. If you are to look at the calculator on your left, that is to be negative 66.7 times 4. So ginawa ko na siya negative kasi transpose ko siya. So 66.7 times 4 divided by 3. So our answer here would be negative 88.93. And this negative symbol right here indicates that it is in compression, since I have assumed my forces to be in tension. So that. And as for this value of EC, I would just be applying summation of forces here. So once again, if I would be copying this to the next slide. Okay, and since you already know the value of EF and BC, you can apply summation of forces horizontal is equal to 0. Or if you don't want them to get involved, you can use summation of forces vertical is equal to 0. And in summation of forces vertical is equal to 0, only AV, this 75 kilonewton force right here, and EC would be affected because your BC and your EF does not have any vertical components. Okay, so from that, it is better if we use this method instead. So by that, summation of forces vertical is equal to 0. let's say upwards is to be positive. So that is to be 66.7 kilonewtons. So minus 75 kilonewtons plus ECX. So ECX. So that should be equal to 0. Okay, so 66.7 minus 75. So 66.7 minus 75, that would be equal to negative 8.3. So negative 8.3 kilonewtons plus, so what would be the x component of EC? So the slope of this line right here is 3:4. So if you would be going back to this slide right here, so this angle right, this slope right here is to be 3:4. So that is 3 and 4. And if you would be applying Pythagorean theorem here, its hypotenuse would be 5. So it is either that you get this angle right here using your trigonometric identities. You're using trigonometry, using SOHCAHTOA, or you can just use these values instead. If you've already watched the previous pre-recorded lecture on method of joints, there is a detailed explanation on what you would be using. Okay, and since I am only concerned with the y component, once again, the slope of this line right here is 3, 4, 5. So from that, I would be using 3/5 EC. Or if you are given the angle, that is to be EC sine theta. So basically 3/5 is equal to sine theta. Okay, so solving for our value of EC, so this should be equal to 0. Looking at the calculator to your left, so I would be transposing 8.3 to the other side, so that would become positive 8.3. Then cross multiplying, that is to be times 5/3. So that is to be 13.83, which is positive. So EC is equal to positive 13.83 kilonewtons, and the positive sign right here indicates that it is in tension. So method of sections would be as simple as that.